we have to finish last steps of the depth reduction, log depth reduction. So maybe we first look at the theorem statement. So theorem statement is this VSBR theorem, which says that if you have a degree D polynomial with circuit complexity S, then there is a log D depth circuit as well computing F, and the size will increase nominally by poly SD or 2 poly SD. So this is of interest only when the degree is not too high. If the degree is exponential, then this isn't an interesting theorem, but when the degree is, let's say, comparable to the size, in that case you are this is proving something very strong. It is saying that in log depth, similar size, you can compute the same polynomial exactly. Some of the details of this are put in the assignment, and the main technique is frontier expansion lemma, assuming homogeneous circuits, and the frontier expansion lemma is this. So it says that polynomial computed at a node u can be expanded in terms of frontier nodes, where frontier nodes are they are below u, and that is the first place where the degree jumped. Let's say it crossed m parameter. So there is one for u and one for the quotient gate. Okay, so we will use these two things. Actually, to expand u, you need the quotient gate, and then to expand the quotient gate, you will need two quotient gates in a summand. Okay, so here you only need one quotient gate, but to expand that, you have to use in every summand, both of them will be quotient gates. So we have to deal with them simultaneously. So in the case when you expand u, you need the degree of u to be more than the parameter, degree parameter, and in the quotient case, you need the parameter to be in between. Okay. So the proof was by induction. This is just induction on the size of the circuit, or you can also think in terms of the depth, induction on the depth. So addition, multiplication are the only two cases that we dealt with, and here we saw that we needed homogeneity assumption. That was important, and we also needed these assumptions here. So actually for the addition gate, it's important that you have homogeneity assumption, otherwise the degree difference can be too large. Okay, so if it is too large, then no matter which frontier gate you pick, it will miss one of the summands. Okay, so you won't be able to apply frontier expansion lemma provably. It will provably fail. So you need the degrees to be very close. So in fact, in this case, degrees will be equal, and then depending on the frontiers, you can get information either side, and the sum will give you everything. This seems pretty important for the proof to work, and some assumptions also needed in the product. So yeah, that was for the frontier expansion lemma. Now to apply this lemma to reduce the depth, we will pick m optimally to be half. So if you want to expand u with respect to frontier gate w, then you want w to be such that to be the node where the degree just crossed half of the degree of u. And we said that this is the deepest, right? So deepest things are the frontier of half. I'm not sure, because I think ultimately everything can cancel out and give you 0. Okay. So that monotonically is a dangerous assumption. Okay. We don't want that. But maybe that can be dealt with. So if it is 0, then that whole circuit can be removed, sub-circuit.
Algorithmically, we can't deal with it, but
existentially, right. Yeah, so maybe monotonicity can be also assumed. Yeah, that's possible because we are only after an existential. Well, we want the existence of a small circuit. So either way, it will work. And right. So then there was this technical point, which is to do with the way we are proving this depth reduction. That if you expand u with respect to this half degree frontier, you will get multiplication Fanon 3. Okay, so you apply frontier expansion lemma once, and then you apply the, I mean, you use the fact, the property that W, since the degree is growing there the first time, it has to be a multiplication gate. So you get left and right children, and you get U expressed as a sum of things which are all product gates with Fanon 3. But this is not enough, so we cannot stop here. The problem was that although the degree of UW is good, small enough, well, okay, for U it is fine. So the degree of all three is less than degree of U by 2, but this using the quotient gate. So later you also have to apply frontier expansion lemma on the quotient gate, and then what you will get is where the problem is. You get this. Here also currently the multiplication Fanon is 3, but WL is something whose degree is not half of the output. So output is U by V, but its degree may be exceeding the degree of U minus degree of V by 2, right? Because the way we use these frontiers, their parameter is between the degree of U and V. It's the mean actually. So that tells you, that does not tell you much about WL gates degree. So what was the solution for this? Expand again. So we expand again, and then then the multiplication Fanon becomes 2 plus 3. It becomes 5. Okay, and that is where we will settle. So we will settle here. Here the frontier gates will be, they will have to do with the WL, and that will guarantee the degrees to be, all of them to be half of the output, which is U by V. Yeah, so these inequalities you can check. They are easy to believe. But this is the rationale for multiplication Fanon being 5. Okay, 5 is a strange number to have, but we get 5 because of this double application of frontier expansion lemma for quotient gates. So that's the structure theorem. It is not only a depth reduction result, but it also tells you something pretty strong about the structure of the circuit. Okay, so let us continue from here. So eventually we reach a case where or degree of U or degree of the quotient is at most 2. Okay, so the degree will become after these iterations. So iteration means that you write U or U quotient V as a sum of multiplication gates of Fanon 5. That is one, you think of it as one step. This step you will repeat many times, and at some point degree of these inputs to the multiplication gates will fall to a constant, say less than 2, less than equal to 2. So when that happens, then this case you solve trivially. So these we can explicitly compute. In depth 2, so in sigma pi. sigma pi or maybe even sigma pi sigma. That will really depend, but definitely less than equal to sigma 3, depth 3 will be enough for this trivial computation, a brute force computation in the end. And how many iterations are there before you reach this constant degree phase? Invariant is that degree of the output is always halving in this one step. So degree is always halving, right? So then if you started, if at the root the degree was d, then this has only log d iterations. So the invariant is that each application of frontier expansion, which is not once but twice if required. So each application of this type of frontier expansions halves the degree, which means, so invariant means that you get log d depth.
You will explain.
Yes, exactly. This is repeated squaring at the level of sum of products, sum of products of 5 things. So depth is log d, and what is the size in this overall process?
Doing sigma pi, so it's for one node, 5 nodes.
Yeah, so with some care you can show that the size is not exploding 5 times or s times every time, because the way we have written it, it seems that every time we have a big sum of products, but if it is a big sum every time for every factor, then ultimately you are blowing up to s to the log d, right? In the worst case that could have happened, s to the depth. But that is not the case, because these frontiers also keep on reducing. So you are actually the frontiers which you are using are well, first of all, they are all disjoint, because in every next, so in the next iteration the frontier is with a lower degree parameter, so it cannot be the same as the ones before. Okay, so they are actually falling. So whatever you see in the current subtree, from there you pick the frontiers. So you can show that overall it is not too bad. It's just poly SD. The size in the end is poly SD. Okay, so this you can also do as an exercise for the algorithmic analysis in the assignment. And as already remarked, this not only reduces the depth but also makes the circuit very structured. So this the final circuit C prime has alternating plus multiplication gates, right? Because you are always using this sigma pi. Here inside also it's sigma pi and so on. So they alternate, and the fan-in of the multiplication gates is less than equal to 5. Any questions? So this is the complete structure theorem for arithmetic, for algebraic circuits. It's a very powerful result, and well, unprecedented in a way, because these things you don't see in Boolean circuits. I mean, it is surprising because so if the multiplicative fan-in is 5 and the depth is let's say exactly log d, then what is the circuit, what is the maximum degree that the polynomial can, that the circuit can compute? It's kind of 5 to the log d, right, which is d to the log 5 equal to d to the log 5. So that seems to be the magical bound which up to which if you go, then maybe you can do some non-trivial computation, but there is no need to go beyond that. If your goal is to compute only a degree d polynomial, then there is no point doing computations which exceed the degree bound d to the log 5. Okay. So d to the log 5 is something like d square. So if you want to attain a polynomial of degree d, then there is no point doing any computation where the intermediate degree blows up beyond this d square. And this is in a way intuitive, but you never know in advance. I mean, maybe it was possible to have intermediate computations which compute something very high degree, and then in the end the degree reduces. That might have helped, but this theorem is saying that it doesn't help. Just a moderate growth is all you require. Okay. So if there are no questions, then we will prove something even stronger. Well, stronger in some sense than this result. So now we will reduce the depth to bare minimum. And what is that? What is bare minimum? So some may think that even log d is too much depth, right? Why not constant depth? Why not 100? So we will ultimately go to depth 3. Okay, so we will say that, oh, well, depth 3 is also in a way enough. But no, depth 3. I mean, talk about the minimum, right? So the bare minimum will be 3. So if you go to depth 2, then you are just saying that you have a mathematical polynomial. It's just a sum of monomials. So there is nothing to do there computationally. But when you talk about depth 3, then maybe computationally you can come up with better identities and more compact representations. And we will say that, we will ultimately show that if you can do something on a high depth scale, then you can also see something non-trivial at this depth 3 scale. Okay, it will not be really optimal as the previous result, but still you will get a non-trivial depth 3 representation of the polynomial. So we will go to depth 3 in the end. So that was a big surprise. It happened not many years ago. Non-trivial means, well, trivial is s to the d. If the degree is d and number of variables is, let's say, well, it is always bounded by s. So trivial will be just write down all the monomials, so it will be around s to the d. That is trivial. So non-trivial could be s to the square root d. Right, that is very non-trivial. So which means that if you actually have s to the d potentially many monomials, but you have been able to compress that into s to the square root d, and those things will be visible even at depth 3 scale. So the point of, I mean, at least one point of all this is that since you have seen this efficient log d depth reduction, so now we know that to prove hardness, results for a degree d polynomial f, it suffices to study log d depth. So if you have a polynomial family in mind and you want to show that its circuit complexity is very high, then it will be enough to show that, assuming that the depth of the circuit is log d. Okay, this will be a perfect result. Whatever you can show for log d depth would apply also to other depths, computing that polynomial f. So why can't we have that kind of a connection to, I mean, with constant depth circuits? So that is the thing that we'll really optimize, and we'll optimize it extremely. We'll go to depth 3 in the end. So for now, now we'll reduce this. Further to, so as Abhibhav suggested, first we settle with depth 4. Okay, so let us first show this for depth 4. So why depth 4? What is it that you can do with depth 4 but cannot do with depth 3? Well, so one vague feeling is that if you have a circuit, no. So this business is not about repeated squaring. This is something much simpler. So why can't you just cut your circuit into top and bottom parts? The inputs are here. The top part is basically computing these polynomials with the inputs that it gets here. So that you can write as a sigma pi in sigma pi representation. So sum of products of variables and constants. And the same thing you can do with the bottom part. So then you have sigma pi representation on the top and many sigma pi polynomials in the bottom feeding into the top, right? So that is depth 4. So you basically we call this flattening. So you flatten the top part and flatten the bottom part, and flattening this flattens the original circuit to depth 4. Okay, so this is the simple thing, is the key idea actually. So we just have to implement this. So if you implement this, then you get the following theorem. So Agarwal, when I showed this just before 2008, then later on it was improved. So it keep getting improved in the next decade. So the version that we will do is the following. Let f be a degree d polynomial computed by a sizes circuit. Then pick a parameter t and cut your circuit in such a way so that the top part or the bottom part computes degree t polynomials and the top part computes with respect to them degree d by t. So then for that will give you the result that f has a homogeneous sigma pi d by t sigma pi t circuit. Yeah, that's the top part. Circuit of top fan-in, which is for sigma, top sigma, that is s to the d by t, and overall size is okay. So this is the version by Tabernas. So you should think of T as square root D, and then you see that any degree D polynomial with a size S circuit also has a sigma pi representation where the multiplication fan-ins are square root D and the size is S to the square root D. Now S to the square root D, as already remarked, this is a highly non-trivial size because brute force would give you S to the D, right. So why is the D being reduced so heavily? So that is a non-trivial representation.
Like, what was the improvement? How did the Agarwal-Vinay version look?
Oh, Agarwal-Vinay did not care about the exponent. They just gave S to the small o of D. But they had some other, I mean that proof has some other advantages, which I will not go into right now.
Not making any assumption about the polynomial f, right?
That it has size S circuit.
Like it isn't homogeneous.
No. Well, homogeneity is kind of,
Assume
you can assume that, yeah, you can think of F as broken into homogeneous parts.
how this would behave if f is not homogeneous.
No, so you think of F as a sum of homogeneous parts, and for each homogeneous part you apply this theorem, you will get the same result in the end. Because I mean this S and D, actually ideally you should think of them as comparable, and this S will change to S times D with the homogeneous parts. So yeah, maybe I should formally define this notation.
What about the fan-in of the other?
No, so top fan-in is already written here, and the 2 pi are already defined. The bottom sigma is full fan-in, S to the T.
Like some sum of products of bounded degree.
Yeah, so this part is just, you can think of this as computing a T degree n variate polynomial. So this is fully expanded, gives you n to the T monomials. More interesting is the top part, this part. So here also the fan-in of sigma is only S to the D by T, when it could have been anything. It could have been S to the D in general. So the existence of a small circuit for F has a meaning even for depth 4 representation. Okay, so whatever magic you can do with more depth, which essentially means that whatever magic you can do at all using algebraic circuits, you can do in depth 4.
It's not like how more keep compressing it will be.
You can what?
So it's upper bound, right?
Mm-hmm.
So this cut,
This upper bound is kind of tight. So there are then subsequent papers that suggest that this cannot be improved.
the bottom part is just cutting it at the T frontier. or
Yes,
something,
yes,
right?
yes.
You just cut there and then you just work with the top part.
Right. Yeah, so this part is d by t degree. So if that much of part has already computed degree relative to the inputs, its inputs, d by t, then the bottom part could only compute maximum degree t. So that gives you, for the bottom part, it gives you pi t, pi with fan in t, and the top part gives you pi with fan in d by t. Yeah, so that will be the basic implementation using the structure theorem we saw previously. So that will be used. This is not independent. And moreover, this is a homogeneous depth 4 representation, which means that well, which doesn't mean anything for product gate, but for the sigma gates, yeah, okay, maybe F also has to be homogeneous, otherwise this is impossible. So, yeah, I have to assume that also. That F is a homogeneous polynomial. So, for an arbitrary F, think of a homogeneous part. And if that homogeneous part has a small circuit, then you can convert it into a depth 4 representation, which will be homogeneous, which basically means that whenever you are adding up in one of these two sigma gates, you always add up polynomials of the same degree.
Sorry, I didn't get what was not possible if F was.
If F is inhomogeneous, then this top sigma, this will also be inhomogeneous. So actually the top sigma will be inhomogeneous, but the bottom sigma will not be. It will remain it will be homogeneous. So instead of saying that, I just let us just assume F to be a homogeneous polynomial computed by some circuit, homogeneous or inhomogeneous, doesn't matter. It can be converted to a homogeneous depth 4, where both the sigma.
Or in a way, if F is not homogeneous, then we will not get a circuit which is homogeneous.
Yeah, yes. I mean, you will just look at the homogeneous parts. For that, this theorem is actually for that. Sigma k pi d prime sigma pi t. What is this model? Right. So this circuit looks like it's a sum of product of polynomials, where the sum adds k many summands, and each summand is a multiplication gate with d prime many factors, and each factor, so this Fij is given to you fully. So Fij is in its trivial representation. So where k is top Fanon, k is called top Fanon, and T is called, you can call it bottom Fanon. And this will bound the degree of Fij's. Okay, so bottom Fanon is is basically a degree bound on these Fij's, these factors which appear in your sigma pi Fij representation. Fij's are given to you in full, is in dense representation. So dense representation is just give all the monomials. No need to compress anything there. And second point is that to optimize the size, just take t to be square root d, because that is when t plus d by t will be minimized, and that will be 2 square root d. Forget the 2 because there is a big O, so it will be s to the square root d. So giving k roughly equal to the size roughly equal to s to the square root d. Okay, which is non-trivial. So it's better than s to the d. So that is the point of this theorem. So now in terms of understanding the hardness of polynomials, the question boils down to looking at depth 4 representations of a very special type, right? So if you have a degree d polynomial, then you want to express, so you want to study whether that polynomial can be expressed as sigma pi square root d, sigma pi square root d, non-trivially. So it can obviously be represented in this way using s to the d size, but can you make it non-trivial? Can you make it s to the square root d size representation? So if you show that you cannot, that representation doesn't exist, then it means what? It means that no sizes circuit exists. If this type of a depth 4 representation doesn't exist for your polynomial, then actually you have shown that no circuit exists for the polynomial of size s. Right? So you have a strong connection between general circuit lower bounds and very special type of circuit lower bounds. Any questions? Okay, so let us go into the proof of this, which is just an implementation of that.
I have a question. So this depth, so the depth reduction result in 3, is it field dependent or field independent?
It is field dependent, or it is a characteristic of the field dependent. Doesn't care about the field per se, just characteristic should be larger than d. This d should be smaller than the characteristic, otherwise, or characteristic can be 0. But if you are looking at a prime characteristic smaller than d, then it gets into trouble.
So basically to go to degree 3, you have to just reduce the sigma pi to just pi. That's what you have to do, something like that, right?
That is one way, but it doesn't work.
Yeah.
So you will see the proof. It's a complicated idea. It will first increase the depth to 5 and then it will gradually reduce it to 3. You will see that. Not today. So
Because flipping directly in 4 is not possible. So sigma pi is simple. So you flip, then it
you are saying that just flip the operators.
I mean,
Oh, that is blasphemous.
therefore it's not difficult.
No. If you are given a sum of all the monomials, you cannot express it as a product of linear polynomials. Sigma pi flipping would mean that you are expressing a sum of monomials as a product of linear polynomials, right? It is impossible. I mean, it is mathematically impossible. Forget the size. For whatever size, it is impossible. Since it is based, this result came after a sequence of papers, so we will just use Ram Prasad's survey version. Okay, instead of going into these papers and what did they do, we'll just look at a really refined version subsuming all of them. So it will just start with where we stopped in the previous result, structural result, that let C be the log D depth circuit computing F. So we directly start with log depth. And we assume the size parameter to be the same, which is S. So we renamed the size. This we can do by the previous structural result. Moreover, we can assume that for each internal gate G in C, we have a homogeneous expression. Basically, that this frontier expansion thing that we use, G equal to G I1 to GI5 for all I cannot exceed the size of the circuit, so it's 1 to S. And so if G is a multiplication gate, then you just have these 5 things being multiplied. If G is a addition gate, then you are adding up several products, each being a product of 5 things coming from the lower layer. So let's call this equation 1. And what are the degree bounds? So degree of Gij is what? Degree of G by 2. That's the important thing. Yeah, and maybe keep in mind that all this could be done in polynomial time. But randomized. That is not important. So whatever we will do hence on will also be doable in randomized polynomial time. So you can actually get the depth 4 circuit also in that much time. It will be explicit.
Polynomial time, even in the previous result, we can assume the monotonicity, right?
Yes, I think so. Yes, yeah, I think that can be assumed. So this equation 1, if you keep applying this, throughout all these levels, that will also give you a sigma pi representation, right? I mean, this is just opening up the circuit. So root is computing sigma pi, and then things below are also sigma pi and sigma pi. So you can keep on unfolding the circuit, and ultimately you will get a sigma pi representation. Or if you stop somewhere just before the leaf, you get a sigma pi representation. What is the size of that? What does this trivial implementation give you? So repeating equation 1 gives sigma pi representation of size how much? Well, if you just keep on unfolding this, then you will every unfolding would blow up the fan-in of sigma, right, by something like s to the 5. So, and you will do this log d time. So this will give you something like s to the log d, I think. More than s to the log d. If you just did the trivial thing. Well, this cannot be correct. We correct this. Each time you are no, it will give you s to the d. So what happens is that if you write GI1 again as sigma product and up to GI5 as sigma product and multiply this to ultimately express it as sigma product, you are also producing a lot more Gij kind of polynomials, and you are unfolding each of them. So ultimately what you get is just the trivial representation of sum of monomials. So this will actually give you s to the d. So you don't want to do this in all the levels. If you do it in all the levels, you will get the trivial result. So the idea here would be that to stop at this threshold of t. So as soon as the degree of Gij falls below t, we stop this process. We don't apply it on Gij. Okay, so we will just truncate this process at a threshold of degree t. So to reach to sigma pi t, so this actually would have given us d by 2. Yeah, actually, even in one step, it's already, equation 1 is already of this type. It's sigma s pi sigma pi d by 2, because g, if the g is the root, then its degree is d. So it is already of this size, this type. So to reduce this d by 2 to t, we'll incrementally open this up. Using equation 1. So if Gi1, for example, if G11 has degree more than t, then we'll use equation 1 on that. So expand out Gi1 as a sum of products, and the degree will half. The degree of G11 will half. So if you keep doing this, then at some point you will reach this threshold of t. But then as you are unfolding and multiplying, you are increasing the additive fan-in. You are blowing it up, right? So we have to analyze this carefully. So let's do that. So for each G summoned, Gi1 dot Gir with some Gij of degree greater than t, expand Gij one step further. And same on G, same transformation. So when you are expanding Gij, obviously you are also getting a bigger fan-in representation for G, because Gij is a factor in the summand of G representation. And so keep doing this, right? So again, if G11 is of degree t, then you expand it, its degree will half in the summands. And if G1 at the same time, if G12's degree is more than t, then also apply it on that simultaneously. But then the problem is that G11 and G12, they are, you're in the summand you have a product of those. So when you increase the fan-in of G11 and G21, and you multiply these things out, the overall top fan in blows up. It squares kind of. That is the price you pay in step 1. But after paying these costs, in the end, where do you get? You get to a point where till all GIJs on RHS have degree less than equal to T. Okay, so in the end you have this original polynomial f computed at the root, f equal to sum of products, where each factor in the product has degree less than equal to T. Okay, so this is by definition sigma pi T representation. Is that clear? So now we have to see what is the size of this guy. Is it still S to the D or something smaller? Is the process clear? So the process does not need any proof. Okay, the process is just continue, just repeat step 1. Of course it has to halt. It cannot go on ad infinitum because the degree is being reduced, in fact halved. Right? So it will stop at some point. So now we want to analyze what happened when it stops. Right? How much of size blow up happened? So each expansion like 1 grows the top fan in by a multiple of S. Because top fan in equation 1 is S. So whenever you apply it on Gij, the fan in becomes S square. So it grows by a multiple of S. We intend to show that this happens at most d by t times. Okay, that will be the crux of the proof. Show that this blow up that is happening multiplicatively by S happens at most d by t times. So that would give you a bound of S to the d by t instead of S to the d. How do you show that? Why should you get d by t? So starting degree was around d or maybe d by 2, and you want to reduce it to t, right? So how many iterations would it take?
Log d by t.
Yeah, log d by t, but that's a different analysis, because that you are doing on, in parallel you are doing it also on other GIJs. So that doesn't give you, it is not that it gives you S to the log d. So okay, we have to, yeah, so we have to do this carefully and show that this blow up is actually happening only d by t many times. So we have to do this simultaneous analysis, that in a product gate, when we are doing this on all the inputs, what is the overall blow up? So in equation 1, if degree of G is, let's say, temporarily it is d prime, then largest degree Gij in any summand has degree how much? What is the largest degree Gij? upper bound you know is d prime by 2, but what is the lower bound? So that you will get by homogeneity, since the degree of the product is d prime. One of them, or the largest one, has to be more than d prime by 5.
It's for averaging, right?
Average.
Right, homogeneity?
In every summand. Summand I. Otherwise, there might be just some very bad summands low degree. You will not have d prime by 5 factor anywhere. The whole summand may have degree, let's say 2. Yeah. So, I mean, just think of a fixed I when I am making these statements, but then I has to vary over all the summands. So, whatever I will say has to be true for all the summands. But in your mind, you can fix I to be 1. Just think of the first summand. So, in the first summand, the largest degree factor has to be at least d prime by 5, and it is at most d prime by 2. That you know. So, moreover, the second largest degree So, what can you say about the second largest? Lower bound. So, if you remove the largest degree Gij, then how much of the degree remains?
At least half, but at most 4.
At least half remains, right? So, that's d prime minus d prime by 2. So, this much remains. And how many factors remain? 4 factors. So, you get d prime by 8. So, the largest degree is at least d prime by 5, and the next one is at least d prime by 8. So, both of them in particular are at least d prime by 8. That is all I wanted. So, it implies that in each new summand, there are 2 factors of degree d prime by 8. So, from this I will deduce that whenever we expand, we use equation 1 to expand. To expand a degree greater than equal to t factor, we introduce at least one more factor So, after expanding by equation 1, in every summand, in every new summand, there is something still with degree t by 8 surviving. Yeah, I don't remember why t by 8 is important, then I could have done with t by 5, not sure, but anyway, so the point is just that when you expand a high degree G, then in the summands, in every summand there is some moderately high degree Gij also present. Let us take it degree t by 8. That is fine. Okay. Um, so even when you are simultaneously doing this on all these factors that have degree at least t, you still end up with t by 8 degree factors, and then by homogeneity I want to claim that hence this operation you cannot do more than 8 d by t many times. Okay, so does that sound right? Let's check that. So by homogeneity, there can be less than equal to 8 d by t factors in a summand of degree greater than equal to t by 8. So if you are looking at a factor of degree t by 8, then it can only have 8 d by t many factors overall. So this means that the number of iterations is bounded by 8 d by t. Is this believable? That will give you that number of summonds in the end is less than equal to s to the big O of d by t. So you have, let's say you start with in the very beginning you have a summand with 5 factors, and simultaneously so all of them say had degree more than t, so you simultaneously applied this expansion on these 5. So each of these will now produce summands of 5 factors. So if you look at the product of these respective factors, then you have 10 factors now. You have 25, and so on. So every time these number of factors keep on growing. But can the number of these iterations be more than this 8 d by t?
Because each iteration you double the number of factors of degree t by 8.
Right. Is the doubling important, or did we only need one?
No, it doubles every time, right? Because we want a total of 8 d by t. So only if it doubles every time can we say that this will happen in. The number of iterations should be lesser than this. It should be the log of this, right?
Yeah, but no, I don't want the log. That log has a mistake. I think I need 2 because there is some reason which I don't remember.
Summands also increase.
No, the summand increase we are analyzing in the end. We don't worry about that. That is the last step. For now, we just want to show that the number of times we will apply equation 1, that is limited by 8 d by t. And for that, the argument is just by homogeneity and the fact that when you apply it once, that equation, in every summand somewhere there is a degree t by 8. In fact, twice in every summand. So even after number of many such iterations, in the end, what do you see? You see that f is equal to sum of products, and if in every product you have, if there were, let's say, L iterations, then there are L times T by 8 contributions in each of these summands, right? And this LT by 8 cannot exceed D. So that should give you the 8D by T upper bound. But once the degree falls below T, then you won't apply equation 1 because then you cannot guarantee anything about the factors. So you do this only for high degree, up to high degree. That's our bound T. So that is one part. That's actually the biggest chunk. Other small thing is that in the end the factors are degree T, and this you will represent fully in terms of sum of monomials in a completely stupid way. So that will further take size s to the T. So finally the degree less than equal to T factors can have at most n to the T or maybe big O many monomials. So combining the two things, this number of summands which is s to the D by T, and within each factor you are expanding n to the T many monomials, so that gives you the product as the size bound. So C converts to sigma pi T circuit with the top fan in s to the big O of D by T and size s to the T plus D by T. Is that clear? Yeah, so that's the result for depth 4. So what this means in terms of lower bound is just look at the contrapositive of what we had shown. So what we had shown is that if there is a small circuit, then there is a small, I mean quote unquote, there is a small depth 4 circuit also. So the contrapositive would say that if for an D degree polynomial f requires homogeneous sigma pi T circuits of size of top fan in fact, not even size. So if you can come up with a polynomial f that is homogeneous and it requires in terms of the degree it requires sigma pi D by T, sigma pi T circuits with top fan in slightly more than that bound. So n to the little omega D by T. So n is the number of variables that also I need. So an n variate D degree polynomial f that requires this special representation of top fan in n to the more than D by T, asymptotically more than D by T, strictly more than D by T. Then what does it mean? F requires arithmetic circuits of size how much? What is the lower bound that you get? Just look at the contrapositive. So if there is a circuit of size n to the big O of d by t, so then you would have done in poly n. So now you get n to the little omega 1. You get super polynomial bound here. Maybe I should add a t as well somewhere. Should I add it here? Right. So, no. So this plus t was for the size. Sorry, the previous thing is correct. Yeah. Just this. Just if you prove something for the top fan in, then you get a result for. Yeah. So what we have shown previously is actually stronger. It is saying that the top fan in the representation is only it is s to the d by t. So in this language, it is if you prove a lower bound of n to the little omega d by t, then that would mean that the arithmetic circuits in general for your f are super poly in the number of variables. Okay, so that's a super polynomial lower bound approach. Yeah, it is still not an exponential lower bound approach. So it will not show that the polynomial is as hard as 2 raised to n, which could be your final goal. But even super polynomial lower bounds are completely out of reach currently. So this is one way to highly specialize that question. You specialize it to just very moderately high top fan in depth 4 circuits and very well structured. So there is homogeneity and everything here. Right. Okay. So